folks. My name is Oscar Spencer. I'm a co-author of the Grain Programming Language, and my talk is a compiler author's guide to WebAssembly GC. So first, let's all get on the same page about what is garbage. So when you're writing a high-level programming language all the time, we write code exactly like this, and we don't think twice about it. But you're allocating just objects and objects all over the place. And it's the job of a garbage collector to go and clean that up for you. Because eventually, your program's just going to run out of memory. And that's pretty sad. We don't want that to happen. So in a low-level language like C, you are the garbage collector. You allocate memory. You have to remember to free that memory. And sometimes that can be a little bit of a challenge. But garbage collectors, they're often super-duper large and really complicated. Like, these are often, masterful pieces of engineering that thousands of engineer hours have gone into to make awesome. Some of them do crazy things like copy memory over to different heaps depending on how old the data is and all sorts of crazy stuff like that. And that can be kind of large. It may be sticking that in your Wasm module is not super cool. So again, if you're a super low-level language like C, this isn't really a big deal. A very small portion of your Wasm module is going to be your allocation code, your implementation of malloc and free. But if you're a high-level language, you got to ship a whole freaking GC in your module. And that's not really ideal, right? Because in the Wasm MVP with linear memory, the runtime just hands you a chunk of memory and says, hey, have at it. Manage it however you best see fit. And if I need a garbage collector, then I guess I got to ship one. But browsers have these world-class garbage collectors, and so it would be amazing if there was an opportunity for WebAssembly code to be able to tap into that. So, goals of the Wasm GC proposal. Provide a way for WebAssembly modules to utilize the runtime's GC implementation, and then make sure it's generic enough that it's going to work for any language. Different languages sometimes want different things out of a GC implementation, but as long as it's generic enough, it should be perfectly fine. And then the big goal is, if you're a high-level language, your WebAssembly module should just be all user code, like no allocator, no GC implementation, no nothing. So this is the TLDR of the Wasm GC proposal, which, if you take nothing else from this talk, I want you to remember this. All the proposal is you can make structs and arrays. That's literally it. And this is kind of brilliant in a way. It's brilliant because the GC proposal doesn't tell you how you have to do GC. That's now left up completely to the runtime. So let's say you're running at the edge. Maybe your functions as a service platform. Maybe the best GC algorithm for you is don't bother GC at all. My favorite GC algorithm is just exit. Just let the program finish and throw it all away. Super happy. If you've got a real-time program running on, say, a robotic arm or a car, when you press the brake in your car, you probably don't want that GC algorithm to be in the way of actually getting the code executing. Some garbage collectors do what's called stopping the world, where they'll pause execution of your program and then go do a bunch of GC and then go back. And maybe that's not ideal for that type of workload. But you can do something like reference counting in that case, where you amortize all the cost of GC over the lifetime of your program. So I think even bigger is the opportunity for portability. You don't have to recompile your WebAssembly modules to make them super portable with whatever type of GC you want. This is particularly huge when you start thinking about things like the component model, right? Because I just want to go download a Wasm module or a Wasm component from somewhere and just go run it. I don't want to have to go and figure out how to recompile it. I can just take an existing one, and so long if it's using Wasm GC, as long as my runtime uses the algorithm that I want, I'm going to be a pretty happy camper. So the Wasm GC proposal gives us a bunch of new reference types. Now, the func reference type and extern was a part of the reference types proposal, but GC gives us this new any type, and then that's sort of the top type for all these new heap types. And then we have EQ types, which are types that can be compared for, like, hey, are these two objects the same thing? And then, as I mentioned before, we have structs and arrays, but additionally, we get I31s. And so I31 is the, hey, this is a value that exists on the heap, but it's not a pointer. It's just a scalar value. The reason why it's 31 bits is because a runtime can efficiently use 1 bit of that value to tag it and say, let's set the last bit of that value to 1. And then now, from the runtime's perspective, it says, oh, I know that this thing is not a pointer. I won't do something scary with it. This is a funny thing for Grain. in particular, because in our linear memory implementation, we did the exact same thing, just in our own implementation. But we also use a little bit, a couple extra bits for more information to handle things like printing. And so we still need that extra bit, so now we're down to 30 bits instead of 31 bits. But it's sort of a fun thing that happens. The fields of structs and arrays can be any of the core Wasm number types, so I32, 64, F32, 64, or any of these reference types. And fields can have a special pack type, so they can be I8s, I16s. And these types were not added to core WebAssembly, so you don't just have new number types that are I8s and I16s. That would complicate much of Wasm. So instead, this is limited to just field types for structs and arrays. And of course, fields can be mutable, so you can have immutable arrays or arrays that are mutable, for like array mute I8, for example, is a buffer type. And additionally, any of your struct fields can be mutable. We also get subtyping. What's kind of neat about how the subtyping works is theoretically, as long as one struct you had, all the fields were a prefix of another struct, the spec says that that is a subtype of that other struct. But for some performance reasons, make sure optimizers don't screw you up. You want to explicitly declare all of your subtypes in your actual Wasm code. And then you can subtype them as many times as you need and say, if you have some data that's relevant to all of your GC objects, maybe you have an overarching type for that. And then for the more specific types, you just add on additional fields. So of course, we get a bunch of new instructions to handle all of this. Of course, instructions to create structs, get the values, set the values in structs. Arrays are pretty similar, same instructions, but we got a couple more. In particular, you can initialize an array from a data segment or from an element segment. And so remember now that we have arrays of reference types, if you had an element segment filled with func refs, for example, and you want to initialize an array from that element segment, you totally can. You can also get the length of arrays, which programmers tend to love to do. And then, of course, there's bulk memory instructions for filling, copying, and all that sort of fun stuff. For I31, of course, we need to be able to create it. And then when you want to get that value back, you have to tell Wasm, how do you want them to handle the sign bit? Do you want to sign extend or not? And then we get to the fun casting instructions. Ref.test lets you say, hey, I have this value. Is it this particular type? Plain and simple, easy. Ref.cast, if you're a compiler engineer, this is your best friend. Because essentially, there's going to be times when you're trying to compile a program where you can prove from your compiler that you know that the value, like the type of this value is a certain type. But for whatever reason, and I'll show you an example of this later, you can't actually compile it with that exact type. This is your escape hash that says, hey, no, we can just cast this value, but this does incur a runtime cost. It's going to actually check that value, make sure it can be cast to whatever type it needs to be cast to, and then if it doesn't work, then it will trap. And so that is something that you do have to worry about. Additionally, we have branch on cast and branch on cast fail, which it's exactly like a ref test with like an if statement, basically, which if you're a fan of the BR table instruction, you may notice there is no BR table on cast and cast fail, which, I'm just going to ride until we get that instruction, but for now, it'll be OK. And then for quality instructions, for EQ types in particular, you can test, are these things the same object? Now, I want to talk about some of the quirks of Wasm GC, particularly if you're trying to compile to it. The first is non-nullable locals. So in WebAssembly up until now, let's say you had a local that was an I32. If you attempt to read that local before you set it, you just get back 0. Great, awesome, well-defined behavior. Now we have reference types, which they can be null, so you could have a null local, and if you ask for the value before you set a value, you would just get back null. But you can have non-nullable locals. And so the Wasm validator actually looks through and checks, did you initialize this local before you tried to get the value? Which that's fine, makes sense. But it turns out it would be really hard to actually validate that quickly, because if we try to look at block scopes, for example, let's say I have a block, inside that block, I have an if statement. One side, I initialize it. On the other side, maybe there's more if statements, and maybe it gets initialized later. Maybe me, as the compiler author, I can prove that that value will always be initialized before it gets read later, but that's a lot for a validator to try and track. So the concession was, we're just going to look at the current block scope and see if it was initialized there. So this WAT here does not validate. So even though on the 5th line here, we are setting this local for the struct, it doesn't validate because it's on block, which that's kind of annoying. This is something that I had to change the grain compiler to handle because we did stuff like this. We would put all of our initialization in a block, things like that, and it's definitely something that you'll probably run into. Next is mutability. The funny thing here is with the type system, I didn't go into creating recursive types, but you totally can create a mutable recursive types, but there's no way to create those values. And a part of that reason is that immutable types are not subtypes of mutable types, which you would think, like, okay, if I'm expecting an immutable array, and you pass me a mutable one and just lie to me and say, hey, it's immutable, you can't write to it, that's probably fine. But from an optimizer's perspective, that's not great. You get into really weird situations of, oh, well, sometimes this actually is written to, and sometimes it's not. So it's not a subtype. So if you're building utilities within your compiler to do certain things, like maybe if you're doing an array copy or something for a specific array type, it's not going to work across the mutable and immutable versions. And our buffer type, array mute I8. This is, in my opinion, the only, I'm not going to call it bad thing about Wasm GC, but one place where we're just objectively worse than linear memory. If you're going to array mute I8 and you want to load or store like an I32 or an I64, you can't. There's no way to do that right now. And that sucks. There's a lot of algorithms that really rely on being able to load and store F64s, which of course you're probably thinking already, well, just make it an array mute I64. It's basically the same thing. But then when you try and load and store I8s, for example, now you have to read the value, you have to set the right byte and all that. So, but there are rumblings of, hey, actually, let's just support this, because this is totally something that can be supported. Now, let's talk about Grain and some of the specifics of me actually implementing this. So, Grain today, it's linear 32-bit memory, great. Our GC is performed via reference counting, which there's more to that than you might originally think of, because yes, we do have to put reference counts on things, but it also means anytime we load values from the heap, we have to inkref them. Anytime values go out of scope, we need to decoref them. That adds a lot to all the compilation that gets into your final program, which ends up slowing you down. And we only leak memory sometimes. The first major consideration in terms of how are we going to get to GC. Grain has fully generic first-class functions. So what this means is we don't do like monomorphization or anything like that. If you have a function that is generic, it will actually compile to a function that takes any value. For example, if you have a list.map function, we want to be able to do list.map. We'd love to take a function, a list of values, and apply a function that transforms those values. But we want it to work on lists of any type as long as they're paired with the function that works on values of that type. What that means, though, is we need, I'll just hop to the next slide here. We need a uniform representation. So with linear memory, all pointers to values are I32s, so that's easy. We can represent that as an I32. Any other value, so maybe like a character or a small number, we need to make sure that that's also representable as an I32 because we need every single parameter type and result type to be an I32. That's the only way we can get the Wasm types to work out at that level. So if I come back here, a much simpler example is apply. And so apply is a function that takes a function and a value and applies the function to that value. And so in linear memory, this is what this compiles to today. You'll see there's a call to decoref, which is the reference counting thing that's happening. The first argument of every function is the function's closure, but we don't need to worry about that right now. That's what's going on there. But the second part is we do a return call indirect. We look inside the closure for the function that we want to call. We pull out the table index that that function is in, and then we're able to call that function. But if you look at the parameters, it's I32, I32 to I32. And that's the only way that we can actually make this work when we want to compile it. So Wasm GC gives us all these rich types for heap values, right? So we can have structs with certain types of fields, arrays of whatever values. But if we use them in type signatures, we're going to run into the same problem as if we had like an F64 that we wanted to pass to a function. It's just not going to work. It needs to have this specific type. So we can use ref any to accomplish this exact same task. So if we take a look at what it looks like in Wasm GC, which it looks like more stuff, but it's basically just more types, we have a function type, which is a ref any and a ref any to a ref any. And then we have our closure, which is our data structure for actually holding values that get closed over, which not super important, so don't dig too deep into that. But if we look at the actual apply function here, one, we're not doing the reference counting anymore. I think that's pretty hot. But besides that, we are actually just able to call the reference. So instead of indexing into a table, we're now using actual func refs, which is pretty cool. But you notice there's a couple of casts in here. And those casts are kind of sad. The first cast is us casting that any type for the closure to be the actual closure type. That one we can probably get rid of. We can just improve the compiler to make that go away. The second one is, okay, well, we have this func ref, and the type of our closure, if you look at that last field, it's just a plain func ref. It doesn't say what the parameters and results are. We need to cast it to the actual type of that function, which is an any to an any. So that one we can't get rid of, but that's okay. Second major consideration. Grain supports generic structural equality. So we have an equality function that does deep nested equality on any values as long as they're the same type. If you have lists or strings or whatever, we can do it. But that means we need to be able to walk our data structures. So in linear memory, this is pretty easy. You have contiguous memory. You have a for loop. You can, let's say you have a tuple. You look at the first value, the second value, the third value, and you compare them. Not really a big deal. When it comes to our new struct types, if I have a tuple with 3 elements, that's a struct with 3 fields. But if I have a tuple with 4 values, it's a struct with 4 values. They're not the same type. If you do a struct get, you have to know at compile time what fields you want to access. You can't dynamically access struct fields, which makes sense. But that means I can't walk those data structures in the same way. I need to compile a function that knows how to walk a struct of a certain type. Or we can do the worst thing, which is model our data a little bit differently. So instead of having a struct for tuples, for example, that has 3 fields for the 3 values, it can be a struct with some metadata and then an array of the values in that tuple. And then we can go back to being able to walk the data structures. The bad news about that, though, is we add a layer of indirection. So instead of just getting the value from the struct, now we have to get the array from the struct, and then we have to get the value from the array. And of course, doing that array access also does bounds checking, even though we know that it's never going to be out of bounds. So that's not that cool, but it's something that we can definitely improve, but it is something that you're going to run into. And the third major consideration is that WASI and the component model only work with linear memory. And we don't want to lose support for WASI and the component model because they're awesome. But guess what? We have free will. Nobody is stopping you from including having a linear memory at the same time you're doing Wasm GC. So this is actually a non-issue. You can totally just write a couple things to linear memory to do WASI stuff. You might have to do a couple of copies, but that's okay. And I originally thought that we'd be able to get rid of the allocator completely going to GC, but we have one trying to do WASI stuff. Maybe you have a simple bump allocator and you just reset every time you do a WASI call. That's fine. That's something you can make work. But we also have some algorithms within our runtime that, okay, if I'm moving to GC, I got to update all the runtime. So we might as well just keep the allocator for now. So not completely off of the linear memory, not completely off of having the allocator, but I did get to delete all of the reference counting code, and so that was pretty good. So what effects did this have on compilation? That's what everyone wants to know. First is binary size. So for an empty grain program, we have a test in our test suite to make sure that we don't regress on making the programs bigger for some reason. An empty grain program, so nothing at all, just module, whatever, no code, that was 3,091 bytes, which is a lot, sounds like a lot. And it's mostly because there's a bunch of initialization code that has to go into every module. And with linear memory, those are writes into a memory that gets exported from the module. So something like Wasm-opt isn't able to prove that that code isn't needed and it stays there. But with GC, we're down to 292 bytes, baby! And I'm like, that's hot. I love that. That's awesome. So this is big news, and that can get even smaller. I looked at what gets produced, and Wasm-opt can go a little bit further. And so I don't know if Thomas Lively is here, but I got to bother him, and we can make that happen. Hello World program. That drops in size by 35%. That's pretty cool. Excited about that. But let's talk about some performance. So, obviously, being a functional programming language, we freaking love linked lists. We love them bad, baby. So this test, pretty unscientific, but it's allocate a linked list with 10 million elements and then reverse it, which basically recreates the list. And let's see what happened with different runtimes. Wasm time, super optimized for linear memory. It's its bread and butter. That was already super duper fast in Wasm time. Going to Wasm GC, it got a little bit slower. That's largely just because, hey, the linear memory is super optimized in Wasm time, and GC just happened recently, so there's probably a lot more tuning to do there. That's okay. Wasm Edge has not implemented it in their ahead-of-time compiler yet. It's only implemented in the interpreter, so don't freak out at the large bars for Wasm Edge. But we see something like a 5x speedup running in the interpreter in Wasm Edge, which is pretty cool. And then amazingly, V8, that beautiful, sweet browser engine that knows how to do garbage collection real good, we see a rapid 10x speedup in performance. And funny enough, you see, okay, it basically just puts it on par with Wasm time, but that's kind of a big deal. That's pretty cool. To get that level of performance when we're running in the browser or running outside the browser in something like V8, it's massive to get those speedups. Next test I did was doing some bigint math. So this was, okay, do 10 million bigint additions, and that allocates a new bigint every single time. Same thing with Wasm time, got a little bit slower. Wasm Edge, similarly, we see that like 5x speed up. V8, you'll notice, the Wasm GC bar isn't even on the graph. When I ran the test, the linear memory version took like 15 seconds to run. And then I compiled it with GC. I hit enter, and it completed immediately, and it had the correct answer. And I was like, suspicious. But then looking into it more, it turns out, nah, V8's just about it. V8's just super fast at doing this type of thing, and I think V8 was able to completely optimize away all of the allocations in that case, and it just basically did a bunch of like I64 math on all the bigints, which I think was pretty freaking cool. So that was the most surprising result that I saw, but I thought it was pretty cool. So to recap a little bit on that, Wasm GC makes the implementation of your high-level languages much easier. All of my bugs with GC, gone. Now it's the runtime authors that have to deal with it, which is pretty sweet. And of course, all the binaries are a lot smaller. We're able to dump way more code because there's way more typing information that the optimizers are able to use. And in a lot of cases, we're running much faster. The ability for your GC algorithm to be selected by the runtime is absolutely huge for portability, and I don't think that that can be understated at all. And then having more high-level languages for WebAssembly is just amazing for our ecosystem and amazing for the component model. Yes, today we don't have that support yet in the component model to do GC in the canonical ABI, but it's coming. But we can do it today and shown it's actually not that bad when you think about, oh no, you have to copy everywhere. If you're printing a list in Grain, for example, the expensive thing is not copying the string to linear memory. It's calling print. That's always going to be the expensive operation there. And of course, that begs the question, what's next for Grain? Well, I got to upstream the GC implementation. It currently exists on my laptop. I didn't even push it up to GitHub. If you want to wreck my whole conference weekend, just pour a cup of coffee on my laptop and it's game over. we need support for Wasm exceptions. So this is something that we hadn't implemented up until now, because think about what happens when an exception gets thrown. You lose your entire stack. If I have values on the stack and I need to manage their ref counts, if you lose your entire stack, I can't do that. Sounds like a hard problem, so we just never tackled it. But with GC, it's not nearly as hard of a problem anymore. Like, you lose the stack, we don't care. The ref counts aren't being managed by us. So we can actually implement exceptions, which means things like, hey, when you're testing your programs and something throws an exception, it doesn't have to kill your test suite, which is pretty exciting. And of course, releasing the initial beta of Silo, which is our build tool and package manager to make it easier for people to manage building grain projects and working with components. And of course, lastly, is improving component model support. We want to help on working out what the canonical ABI for GC should look like. And we're really excited to get involved on that. And so with that, thank you so much, folks. That's my talk. And I somehow made it in time for a couple of questions, and I have way more stuff that I could not fit into this presentation that I would love to talk about. So if folks have questions, I can answer those now, or you can totally find me later, and I'll answer them then.
Thank you for your presentations.
Absolutely.
So my question was, one of the first slides was suggesting that there was no memory management code at all. That's for garbage collection, that's fine. What about C and C++ programming languages, like you using malloc and free? That hasn't moved away from the runtime, did it?
No, so in those examples, you're still going to have your malloc and free implementation. We ended up still having our malloc and free implementation, but we were able to get rid of the rest of the memory management stuff.
Okay,
yeah.
Thank you very much.
Yeah, absolutely.
Hello. Do you benchmark against JavaScript?
I have
because in the small examples, I guess you could, yeah.
Yeah, no, I haven't benchmarked it against JavaScript just yet. I expect the reason why it's able to go so fast is because JavaScript is the exact type of language that does lots of these tiny allocations and things. So I think the GC is really tuned to that, which is why it performs super well, but I haven't done those comparisons yet. It'll be really interesting to see, because I do think... What else could be done? Yeah. Yeah, absolutely. I think it'll be really interesting to see. Obviously, we've been in this long battle of Wasm versus JS. Like, turns out JS is super fast. Is Wasm actually faster? And I think this is a case where we could maybe get faster than JS because the engines are so optimized.
Yeah, the point is, yeah, the most saying that it could show something that maybe there's space to optimize or stuff that could be done better, or maybe not, or say this is the best we could get or some at the moment.
Yeah, absolutely.
So you mentioned that for the structural equality comparisons, you have to emit like a different walk for every type that you're operating on. How reasonable do you think it would be to have Wasm have a built-in structural equality comparison instruction that reflects on the types?
I don't think so. From a technical perspective, it's certainly possible. But I think from a Wasm perspective, it's not something they'd want to implement because, as Andreas Rosberg says, you want to go as low as possible and no lower. And there's like the weird cases where equality is strange. Like, so let's say you have a nested object and there's float 32s in there, and then you're trying to do equality on them. Do we all agree on what the equality should be in those situations? It's kind of dependent on your implementation and what you want to say is what numbers are actually equal. So I don't think it's something that will actually get implemented, which is a little sad, but I do think we could get some type reflection-y type stuff that might make it easier to do that. But I had thought about this a little bit, and I think you can get away with adding a handful of functions and not one for every single type a user defines. So we'll see what happens. Awesome. With that, thank you so much, folks. Appreciate it.